So look what we wrote on this side.
Would be average rate of change.
The average rate. What do you think I should write here? Look what we wrote here.
So it's 200 and 300.
That's it. Awesome. That's it. So this is the average rate of change between the points with a weight of 200 and 300. Whatever the answer is. They're not asking us to determine it. They're only asking us, oh, yes, they do want us to determine it. So let's determine it then. Awesome. Because I already have the function in. See? Here it is. Second in table. And I go back to the next one. And I punch in 200. And I punch in 300. And all I have to do is copy. And 257.2 minus 148.18 divided by 300 minus 200, which is 100. Good. So then I go to second and exit out from there. And all I have to do is write the left parenthesis, 257.2 minus 148.18, close, and divide by 100. And this is the rate of change, which is 1.0902. It has two measurement units, the same measurement units as before, but between two other points. Any questions? Any questions? That's all I had to say about 1.3. So let's continue with 1.4. Okay, 1.4 really deals with two concepts. I'm going to write the title in the next few minutes, not just now. In the next section, we're going to look at two important concepts. Two important concepts. Okay, so far that we've seen. Can anyone give us one important concept that you can think of? Just try and think of what we looked at so far. Something huge that we said, we did this and we talked about it and talked about it and talked about it. I'll give you a hint. It's an operator. A big operator that we just talked about it and talked about it.
Radical?
Yes, but it was a bigger operator, was new to us. We've never, yes, that's it. So I'm going to write that. Excellent. Good. So one super important is the LIM. Awesome. Okay, the trend. Okay, what is the other important concept that we looked at for polynomial functions, for rational functions, for radical functions? Something. What is it called?
The instantaneous rate of change.
Very good. It's the difference quotient, but that's what it is. Yes. It's close, not exactly. Excellent. So the difference quotient. Now, the reason why we discuss this for several functions and the reason why we discuss this for several functions is because now we want to put them together. And you can say, what are you talking about first? Does anyone remember what is the formula for the difference quotient? And I'll write it here. Very important formula. It starts with the rate of change, right? That's how we developed it together. Anyone?
F of x minus h in parentheses.
F of x plus h, very good, minus
F of x.
minus f of x over? Brilliant, that's it. Thank you very much. Excellent here. Good. So you're saying, how are you going to put these two together? There are two important concepts. So you're going to put the limit in front of this? Yes, that's what I'm going to do. I'm going to put the LIM when h approaches 0 from, I don't know who this person is, so I think it was a mistake. Okay, so f of x plus h minus f of x divided by h. So you can say, what do you mean by h approaches 0? Okay, if you remember when we first discussed the difference quotient, this is what we did. So this was the function, and we had here x. Very close, we had x plus h, but I zoomed in because I can't explain if I don't have some room in there. This was our p, this was our q. They were very, very close to each other. They were like this, close to each other. Not the same thing, not the same point. Then we said that this is f of x, and then we said that this was f of x plus h. And I think Sierra said, well, this is almost, because P and Q are so close, this line, this slope, was giving us almost the instantaneous rate of change. That was perfect because that's what she remembered. She said, oh, this is almost. But now, hear me out. If Q gets closer and closer, it's already close, but gets closer and closer to P, what will happen is h approaches 0. So the slope of this line is this. But if I put the limit in front, as h approaches 0, I'm asking, find the trend of the difference quotient. The trend of the difference quotient will give us the instantaneous rate of change. For sure, not almost anymore. And this has a name. It's called f prime of x. How do we call this? So f prime of x is the two important concepts put together. It's the exact, not almost anymore. It's the exact instantaneous rate of change because I put the limit in front of it. The limit says, where is this going? Well, when h approaches 0, this will become the tangent. And the tangent, the slope of the tangent gives the instantaneous rate of change. So we have to write this. F prime is nothing else but, so f prime of x is the instantaneous rate of change of f of x. This is not entirely correct. I have to continue with something very important that I want to talk about it right now. So f prime is indeed the instantaneous rate of change of f of x, comma, when f prime exists we don't really like to say f prime exists, but we like to say when f of x is, and this is a big word now, differentiable. This is a big Scrabble word if you want. I don't play Scrabble normally, but okay. So when is a function differentiable? That's next in our discussion right now. So what we did so far. So now I can write the title. Differentiation using limits of the difference quotient. Or difference quotients. Okay. So 1.4, it's differentiation. We don't know what this means yet. Using limits of the difference quotients. Okay, so we put these two concepts that we've been talking about for 3 weeks almost, the LIM and the difference quotient, we put them together. And now this is not almost anymore. It's the exact instantaneous rate of change. How fast is the function f changing at any particular instant? But at that instant, the derivative must exist. So when the derivative does not exist, when the function is not continuous, when it's jump or infinite discontinuity or removable, and there is another way in which it's not differentiable. So I can determine the rate of change of a function at any point if its derivative exists at that point, or if the function is differentiable at that point. So not differentiable. When is the function not differentiable? Number one, when it's not continuous. And there are other situations. Cusp or corner. What does this mean? Well, a function, this is like between two teeth. The function is continuous at this point, but it's not differentiable. Why? Because it has an infinite tangent, a tangent with a slope that is infinite. What about a corner? Remember we said unique tangent. So what's wrong with the corner? Well, I have to follow the function. This is one tangent, and this is another tangent. I can't say, oh, why don't you put the tangent here? I can't. The tangent has to follow the function. Here it doesn't follow the function. So here there are two tangents. When it has a corner, the function is not differentiable. At this point, it does not have a derivative. If you ask me, find the derivative or the rate of change at that point, I'll say, sorry. It doesn't exist. Okay? So another one is what I just said, vertical tangent. In a different way, so something like this. See, at this point, the function has a vertical tangent. Okay, vertical tangent right here. So let me just say, 1 second. Ingrid, I did not send you the link. We don't meet before 8:30, okay? So wait for me to send you the link in an email. Ingrid, did you hear me? Hello? I guess she can't hear me just yet. She will. Okay, very good. So I'm going to share my screen. Ingrid, we haven't started. We said 8:30, please. This is not the link for your class. I'll send you the link, okay?
Okay, sorry about that.
No worries. I said wait till I send it to you in an email. I will.
Okay.
I will
All
not
right.
forget. This is a different
All right.
class. Thank
All
you. See you shortly.
Okay.
Okay, so let's analyze a couple of graphs here. Let's start with, and also we can look at the difference, the limit of the difference quotient. But let's analyze a few graphs. Let's say for each graph, list all x values for which the function is not differentiable. In other words, if you ask me to tell you the rate of change at that point, I will not be able to. Okay, so can anyone tell us if at x0, the function is differentiable?
Yeah.
Yes, the function is continuous and it does not have a cusp, it does not have a corner, and it does not have a vertical tangent. Awesome. What about x1?
No.
No, because it's continuous, but it has a
Vertical tangent.
corner. Good.
Oh, yeah.
Corner. What about x2?
Yes.
Yes. What about x3?
No.
Because it's a corner. It has two tangents. Awesome. What about x4?
Also no.
No, because it's not continuous. Awesome. What about x5?
No.
No, because it's a corner. What about x6?
Yes.
Yes. Continuous, no corner, no cusp, no vertical tangent. What about x7?
Nope.
No. Why?
It's a jump.
It's not a jump. It's a removable. It's called removable. It's not continuous. Is this okay? Is this okay with everyone?